Welcome back, guys. I hope that you watched the first video. We will continue our discussion on the same topic. Again, we had these two scenarios in the beginning and we tried to understand the physics behind the first scenario. And this is known as natural precession. Then what is this? Exactly, it is known as forced precession. We are forcing the spinning axis to change its direction with the help of a mechanism which consists of a combination of gears. Now we come to that question that was asked in the end of the previous lecture. Will the angular velocity of fan's blade and its oscillation about the vertical stand create a couple? Did you think about it? Did you search for the answer? If not, no problem, we will discuss it in this video. But before that, if these omega and omega p creates a couple in the system, we have a serious problem in it. An aircraft traveling in the air taking a right turn or a left turn. A huge ship executes a pitch or a yaw or a roll. A two-wheeler taking a turn. All these examples have something in common, and that is rotating parts, either in the form of engine or propellers or wheels, etc. As in the case of an aircraft, it is the turbofan engine, maybe a single engine, two engines, three engines, four engines, and maybe up to six engines, or with a turbo propeller series with a single engine, two engines, three engines, or even four engines. As in the case of a ship, its diesel engine is so massive that its crankshaft looks like this, and its massive propellers which rotates at 60 to 70 rpm, which you can see in the pink circle. To the extent that if it generates a couple, it affects this comparatively small gear mechanism. Let's see what's happening. We have a disc rotating about the x-axis in clockwise direction, and along with that, the axis of spin is precessing about the vertical z-axis. Using the right hand thumb rule, the spin vector is pointing in the negative x direction, whereas the precession vector is pointing downwards in the negative z direction. The resultant of these two vectors create an unbalance in the system. Since we are forcing the spin axis, it cannot stop by its own. Over the time, this unbalanced resultant vector appears as if rotating about the y-axis, or in other terms, the vector executes a clockwise rotation. This resistance generated by the system is known as the gyroscopic couple. And using the right hand thumb rule, the couple vector points in the negative y direction. Again, the table we discussed in the previous video is equally applicable in this case as well. Let's look into a practical example. An aircraft, the engine of which is spinning in clockwise direction from the front view, is taking a right turn as shown in the slide. Axis of spin is negative x since it is clockwise. Precession is clockwise from the top view, So the vector is pointing in the negative z direction, and the gyroscopic couple will be in the negative y direction, or the couple is clockwise in direction. This gyroscopic couple tends to raise the tail and lower the nose. But from the very beginning itself, we were telling that this couple is a serious problem inside the system. How's that? This gyroscopic couple is acting directly on the bearings and supports of the rotor. If these mechanical components are not designed to take up these additional torques, they will eventually fail. So the supports and the bearing do generate an opposite and equal amount of couple known as reactive gyroscopic couple, which will tend to do the opposite of what gyroscopic couple did. In this case, the reactive gyroscopic couple is anti-clockwise in direction and tends to raise the nose and lower the tail. We can add one more row in the table for reactive gyroscopic couple. As for a ship, in the beginning we saw three kinds of motion. First one, pitch, which is a movement about the central transverse axis, the yellow color. Yaw, a movement about a central vertical axis. And a roll, movement about the longitudinal axis. In roll, since the rotor and the longitudinal axis are parallel to each other, no precessional motion takes place and hence there is no gyroscopic effect in it. But for the other two cases, that is force, pitch and yaw, the axis of spin is changing its direction, which results in gyroscopic couple. For example, the ship taking a turn like this, which is technically referred to as a yaw, develops a gyroscopic couple. As is clear from the picture, x is positive from the front view, precession is clockwise or otherwise negative z, the gyroscopic couple would be positive y, and the reactive gyroscopic couple is negative y. Finally, the mathematical relation relating the angular velocities, the mass and the gyroscopic couple is given by c is equal to I omega omega p, where c is the gyroscopic couple, I the mass moment of inertia of the disk, omega the angular velocity of spin, and omega p the angular velocity of precession. We will try to discuss the derivation of the expression in a separate video. That's all for today. Thanks for watching.